I did not ask you to watch a video, did I? Did anybody watch it? That's okay. I'm going to go through it. This is a very important concept, so I'm going to go through this. We'll see how much of 2-1 we can get through today. There are a lot of notes for 2-1. All right, let's get going. Are we ready to move on? I feel like, we need to officially say, okay, test is over now. Okay. All right, so we are going to now get into Chapter 2 called Derivatives. So if you were to ask someone who finishes Cal 1, what's Cal 1 about? First thing probably come out of their mouth is derivatives after a couple of bad words. And then they say derivatives, right? So this is really the core of what we're going to be doing in here, but it's all based upon the limit. So the limit that we did is going to be needed for this section, but it's a new concept, this idea of a derivative. So we study this thing, we studied the limit, now it's going to lead us to this thing called the derivative, which is going to help us do some really cool things geometrically in physical situations. We'll be able to look at velocities of things, of objects. In the end, we're going to be able to solve some very difficult problems that you couldn't do in college algebra with this idea of a derivative. So you just have to stay tuned. But it all starts with the idea of a tangent line. So we know hopefully from some geometry in the past that we define a tangent line by using a circle. And we say, all right, if you have 2 points on a circle, if you draw a line between the 2 points, we call that a secant line. And if you imagine moving that blue point over across to the black point, eventually when you put the blue right on top of the black one, you create this line that just touches the circle at one point, right? And that is a tangent line. What we're going to do is extend that idea to a function. So instead of using a circle, we're going to use a graph and try and still come up with this idea of a tangent line. So we will have 2 points on the curve. Right now, if I have 2 points on a curve and I connect them with the line, we would call this a secant line, just like we did on the circle. And what we want to do is pull that point along the curve until it gets closer and closer and closer to the black point. And then once I get right on top of the black point, right there, I have a line, the green one, and that is called my tangent line. All right? That's the geometric idea of what we're going to want to do. Now, I'd like to pull this point out a little bit. I'd like to zoom in, so I'm going to zoom in right into this little region. Right? Now, I can get as close as I actually want to that black point, right? I mean, like, I can get infinitesimally close. Once I get on top of it, and it's the same point, then that's the tangent line. But that's kind of weird, right? Because to define a line, how many points do you need? To define a line, you need 2 points, right? If I just give you 1 point and tell you and ask you what's the line through that point, there's infinitely many lines. So you have to have 2 points to have a line, and we're saying that there's some way we're going to be able to get a line through 1 point. It's kind of a weird idea. All right, so that's basically what I said. You move the point over on the curve and it creates the tangent line. Let's go back to college algebra and remember some stuff about equations of lines. All right, this is college algebra review. If someone gives you a point, let's say we call it x1, y1. Let's just say it's the point -1, 2, right there. Someone gives you a second point. Where is it? Oh, there it is. We call it x2, y2. It has the coordinates 5, -4. Once we have the 2 points, we can define a line through them. The slope of that line is defined to be rise over run. The rise would be the change in the y coordinates. Do you remember ever seeing rise was the y2 minus y1? Right? y2 minus y1 is the change in y. In this case, our y2 is what? What's our y2? -4, and our y1 is 2, so I'd do -4 take away 2, that would give me -6. So this rise is actually negative because it's going down. So my rise is -6, and my run would be my change in my x-coordinates, which we would say is x2 minus x1. So you take your x2, which is 5, you subtract your x1, which is -1, you get 6. And then you have the slope. Okay, let's just, y'all look stunned. I don't know if it's just because it feels like Friday or something. Are y'all okay with this or not? Rise over run, y2 minus y1 divided by x2 minus x1. So if I do the rise over run, that gives me the slope, yes? We usually use the letter m for slope, didn't we? So the equation of this line, do you remember this formula right here? Y minus y1 equals m times x minus x1. Remember that formula? This is what we call the point slope form of a line. If somebody gives you a point, x1, y1, and they give you the slope, then you can define the line. So in this particular problem, what was our slope? It was this divided by this, right? So -6 divided by 6, which is -1. So I replace the m with -1. I replace x1 with x1, which was -1. I replace y1 with 2. And then I have the equation. I just move everything to one side, and I have my line. I'm sorry that's so small. I don't think this will make a difference if I make this bigger. Yeah, that helps a little bit, doesn't it? A little better, a little easier to look at? Okay. So, back in college algebra, someone gives you 2 points. You can find not only the slope of the line through the points, but the equation of the line through the points. 2 different things, right? Slope's one thing, equation's a different thing. So now what we're going to do is we're going to look at a graph right here, specifically 3x cubed minus 5x. We're going to find the equation of the line through these 2 points, -1, 2, and 1, -2. So visually, I have this point, -1, 2. I have this point, 1, -2. I'm trying to find the equation of that line. So I compute my rise. I compute my run. So what would the slope of this line be? -2, right? -2. I'm going to take my rise, -4, divided by my run, 2. I should get -2. So the equation of the line should be this. Replace the m with -2. Replace y1 with 2. Replace x1 with -1. And then do your little cleaning up. Move everything to one side. You have the equation of this line. Y equals -2x. So there's really, at this point, there's nothing new. I mean, this is college algebra still. Now, what if I do not tell you what the points are specifically? So I don't tell you it's -1, 2, and, what was the other one? -1, 2, and 1, -2. What if I don't tell you what those are? Is there someone there? Hi. Tests are up there if you want to grab your test. In other words, what I'm doing is I'm leaving these points arbitrary. So here's the way I'd like for us to look at it. Instead of calling it x1, y1, and x2, y2, let's call the x1, let's call it a. All right, a is just some number. And then the y-coordinate would be whatever the function's value is at a, wouldn't it? Whatever a is, plug it into the function, that would be your y-coordinate. And then the other point, instead of calling it x2, y2, let's call the x-coordinate x, and let's call the y-coordinate f of x. If we do that, and just all we're doing is changing letters, we're not doing anything different visually, what we get is our first point is called a f of a. Our second point is called x f of x. The line between them is defined. The rise would be this. It would be this y coordinate, f of x, take away this y coordinate, f of a. So it would be this right there. Do you see it? F of x minus f of a? That's our rise. What would the run be? What's our run going to be? This x minus this a. So our run should be x minus a. What would the slope of this line be then? F of x minus f of a over x minus a. So this, right? So notice the way I abbreviated this. The slope of that secant line, because it connects 2 points, is f of x minus f of a over x minus a. This is all in the notes. Y'all know these notes are online, right? In Canvas, all right. So that is a big definition we're going to have now. The slope of the secant line through 2 points is this formula. Now, what's the equation of the line? So I'm going back to this. I'm referring to the Grandmaster formula for lines. That's our form. Can y'all see that? That's so. What is what's our m in this problem? What's the slope of this line? It's this ugly thing, right? It's this whole ugly thing. If I replace the m with that whole ugly thing and then leave the formula the way it is, I'm also going to have to replace, let's see, x1, I'm going to replace it with what? What did we call x1? It was a. I'm going to replace y1 with f of a. So this is what the formula should look like. It should be y minus f of a equals that ugly slope ratio there, x minus a. So here's our formula. This is just the same thing I'd said in the pictures all written down. There are 2 points. There's the slope of the secant line, which leads to the equation of the secant line. Now, how are we going to use the secant idea to come up with the tangent line? Because remember, the goal is to try and get the tangent line. That green line, we're going to use the secant line to do it. So let's see if we can visualize this. So I'm going to take my first point, AF of A, my second point, XF of X. I draw a secant line between them. And now to try and get to the tangent line, didn't I have to move that blue one over? Yes? Move it over, move it over, move it over, and then I get to it and I put it right on top and we have a problem, right? Why? Why? Let's see. If your first point was AF of A, right, and you slide this thing over and they put them on top of each other, then isn't this point also AF of A? And so doesn't this ratio become, instead of f of x minus f of a over x minus a, doesn't it just become 0 over 0? And the slope wouldn't be defined? I mean, do you see that? That issue is created when you try and drop that point right on top of the other one? So here's the workaround, right? This is the way we're going to get around this. We are faced with something that as we move it closer, gets closer and closer to this form 0 over 0. Well, hey, didn't we just spend almost 4 weeks talking about when things try and become a form of 0 over 0? Yes? When we took limits, we were getting 0 over 0, but we were still able to get answers. And it's obvious, hopefully for you geometrically, that that secant line is approaching a specific line, right? It's not just like randomly going everywhere. That green line looks like it was defined. So the way we're going to be able to get this is to somehow apply a limit. We need to use a limit to get the answer. So let's see how we do it. The slope of the tangent line, this should look familiar, right? What I did in blue there, that's the slope of the secant line, right? The only difference now is that I've thrown this little limit in front of it. What does this limit have the effect of doing? Look at what it's doing. Limit as what goes to what? X approaches A. X approaches A. So going back to our picture here, when I was moving this, the X here is my X coordinate, isn't it? I want that X to slide over towards this one's X coordinate. What's this one's X coordinate? A. So, wait, you want me to let X get close to A? That's what you want me to do? To move that point over? Let X approach A? Okay, then we're going to have to evaluate a limit as X goes to A to figure out what happens, which yields this formula. Now, we have to be careful because we've also seen sometimes limits don't exist, right? If the limit exists, if that limit exists, then the slope will be defined. All right, can you please let me know whether or not you're following this? I mean, like, the visual concept here is okay or not? Any questions? So we're letting X get arbitrarily close to A. This was just the same thing, okay? Except this time when I slide it over, I'm not going to have the problem and go, yay, I've got the tangent line, because I'm going to do a limit to get it. I'm not going to try and actually do 0 divided by 0. So here's the definition. The slope of the tangent line at any given point, m tan, is this limit. Now we call that the first version. All right, this is going to be the first version. So what is this again? What did I say this was right here? This limit is the what? It's the slope of the tangent line, yes? Now, slope is one thing. Equation of tangent line is something different, isn't it? So this note says, okay, well, if you're going to be able to find the slope of the tangent line, then you should be able to give me the equation of the tangent line also. I'm still going to use this formula, this one right here, except we're going to be replacing this m with what? That whole thing. The slope is a limit. The slope is the limit. And that gives us the equation of our tangent line. We're going to do an example, don't worry. I have no idea what this one does. Hold on. I don't think there's any difference here. Oh, okay, no. The only difference is actually when I get there, slide it all the way. I just threw the actual equation in here. Okay, so that's the equation of that tangent line. Example time. And let's do this. Let me see. I want to do this function right here. Come on. -1. 3x cubed minus 5x. 3x cubed minus 5x. Y'all with me? 3x cubed minus 5x. Find the equation of the tangent line to that function f at -1. What is it? -1. Plug -1 in there, you get 2. All right, here we go. Now I'm doing this problem Because that problem right there is exactly this picture. This is x cubed, what was it, 3x 3x cubed minus 5x. This is the graph of 3x cubed minus 5x. This point right here is the point negative 1, 2, all right? So we are going to actually find the slope of that green line. And not only the slope of it, the equation of it. Here's how we'll do it. I first start this problem, since I'm trying to get the equation, I know I'm going to need the slope, yes, of the line? So I need to first find the slope of the tangent line. The slope of the tangent line, by definition, is the limit as what? X approaches a of f of x minus f of a all over x minus a. So let me ask you this. Do you know what a is here? Do you know what x value you want to go approach? I'm sorry, a value. You want your x to go slide towards something, right? What do you want this x value to slide towards? The x coordinate, right? Do we know this x coordinate of this point? Negative 1, right? This right here, this negative 1 is your a. That's where I want to go towards, right? That x coordinate. So just make a note to yourself here. This number right here is a. So what I'll do is I'll rewrite the entire thing. Limit x approaches not a, but negative 1 this time. F of x minus f of negative 1 over x minus negative 1. If I can figure out what this limit is, then I will have the slope of that tangent line. Right now, let's see what happens if we let's do like we've done with every limit. We've just tried to plug in. Just plug in right now negative 1. F of negative 1 minus f of negative 1. 0. Negative 1 minus minus is plus, so negative 1 plus 1, 0. We have 0 over 0, which means we're going to have to do some algebra, right? Eventually. But first, let me figure out what the top left and top right-hand corners of these things are. What is f of x? 3x cubed minus 5x. So let's just replace the top left corner with 3x cubed minus 5x. Do y'all agree? Okay. Now, I'm going to take away from that f of negative 1. So plug negative 1 into the function. It's going to spit out what? 2. It should, because that's what this point meant, right? You plug in negative 1, you get 2. So it should spit out 2. All over x plus 1. Now, if you plug negative 1 in right now, you're going to get 0 over 0. So I'm going to just draw an arrow that we check that 0 over 0. Do I need to check it, or you believe it? You believe it? Okay. So what do you do if you have a limit and you get 0 over 0? What do you do? Do something, algebra or a trick, right? Algebra or a trick. Any ideas? Factor the top. How? I agree, but how? You can only take an x out of the first 2 terms, which would not allow you to do any canceling. Do you remember how when we had like limits and we had h on the bottom, we always want to get the h to cancel because it was the thing that was going to 0? The thing that's going to 0 here is x plus 1. That whole thing is going to 0. I would love for that whole factor, x plus 1, to cancel. But that means I need to be able to break this up here into factors, and there could possibly be 3 of them, because it's what? Cubed? And hoping that one of those is what? X plus 1. So now you're faced with a question here, and I'll stop for a second. I'll say we, I'll include myself in this. Can we factor 3x cubed minus 5x minus 2? Yes or no? All right, so now let's test your college algebra. In college algebra 1414, if you're trying to factor a polynomial, third degree polynomial here, this is not a quadratic. If it was quadratic, I'd be happy. It's cubic. Then there's several approaches to try and do it. How many of you remember the zero factor property where you use this thing called like the synthetic division with the rational zeros, trying to figure out what numbers, that ring a bell? Let me start doing it, and you tell me if this makes sense, all right? So, what is it that I'm really hoping is going to be a factor of this? What's my hope? I'm hoping that there's 3 factors. One of them is x plus 1, correct? That's what I'm hoping for. If x plus 1 is a factor, then x equals -1 is a 0. Meaning if I plug -1 in up here, I should get 0, which I do. So I know this has to be a factor, okay? This must be a factor of this. Does that make sense to you or not? Because when I plug in -1, this goes to 0, means that somehow when it breaks down, this would have to become 0, which means plug in -1. This should work. How can I get the rest of it, though? There's so many different approaches to this. I want to see if anyone here has any idea of how to do it. Because if not, I feel like I'm working with a blank slate and I can just show you whatever I want to show you, right? No suggestions? All right. If there's no suggestions, let me just show you what I think will be the cleanest, easiest approach. We could use long division. Do y'all want to use long division, or does long division is one of those things that you don't like to hear? Yeah? I'll do the other way first. See if you like it or not. Okay, I'm going to create a synthetic division box. I'll ask you if you know what I'm doing in a minute. Then I'm going to identify the numbers, which are the coefficients of this right here. So I have a 3 in front of x cubed. What's in front of x squared? 0, because there is no x squared. What's in front of the x term? Okay, the constant, -2. Now, outside the synthetic division box, I'm going to use the number that I know creates 0, which is -1. And then I'm going to do synthetic division. So I'll ask you if you've ever seen synthetic division, yes or no. All right. All right, that's encouraging. So now what I'm going to do is do the synthetic division. So I bring the 3 down, right? That's 3 here. I multiply and bring that up and put -3 there. Then what? Add down again. That gives me -3. And then multiply -1 times -3. Put that here, which gives me +3. I add down. I get -2. I multiply across again, and I get 2 here. And then what's at the end? 0. And that 0, that last number here, was always the what? The remainder. So we like to kind of peel it off and separate it. Okay. Now there's something very nice that comes from this. And it has to do with these 3 numbers. That's right. The original polynomial started out as x cubed, right? This right here is what remains when we divide by this factor. So let me just write down. What we're saying is this is a 3x what? Squared minus a 3x minus a 2, isn't it? So that's all I need. At this point, I am good to go. Let me show you why. The result is this. The original thing that I was trying to factor on top, which was 3x cubed minus 5x minus 2, that was the original thing I was stuck on, right? I know right now for sure it factors to be x plus 1 times something, right? And I was thinking it would be two things. I actually can just write down this is a quadratic, right? If I multiply it by this and distribute it and do all that, I get back this. But what I've done is I've peeled off the x plus 1, which is going to allow me to cancel it. Do you all see that? All right. I'm done with my trying to attack that. Let me get back to the slope of the tangent line. So the slope of the tangent line was equal to the limit as I was letting x approach -1 of the numerator, which I just factored using this synthetic division thing, over the denominator, which was x plus 1. And they cancel, right? And now that limit is no longer going to give you 0 over 0. And that's a good thing, right? So the limit as x approaches -1 of whatever was left is, so plug in -1. Bless you. 3 plus 3, bless you, minus 2. So 4. This right here is the slope of that tangent line, 4. I'll recap. We're not done. All we found was the slope of tangent line, right? We're not done. So let me just recap this thing. We started with this. We said, oh, okay, here's the formula. We plugged in. We said, oh, crap, this is not a quadratic. How do we break that down? Well, I know x plus 1 has to be a factor because when I plug -1 in, I get 0. Then I said, all right, how about rewriting that polynomial in a synthetic division box, coming in with the 0, right? The thing that creates 0 here, -1, doing synthetic division, making sure I get 0 out here. These three numbers represent the coefficients of the remaining polynomial. That means that the original polynomial breaks down to be the x plus 1 times this. Rewrite the limit, factored, cancel, get the limit. Are you still alive? Okay, give me a vote of confidence here. Speaking of vote of confidence, am I recording? Yes. Okay. Love it. Yeah. So, how's my vote of confidence over there? It's okay. 22. We'll move on. So we have the foundation. We have the tangent line, right? The slope. Now we need the equation. So this is just one little subtle thing. We've got to use this formula right here. Y minus y1 equals m times x minus x1. The slope right here is our tangent slope that we just got, which was what? 4. Our y1 is 2. Our x1 was -1. So just plug and chug. Y minus 2 equals 4 times x minus -1. Y minus 2 equals 4 times x plus 1. And we always like to isolate the y. Why do you think we like that? Why do you think we like to get the y by itself? Just because we like to? It's just because this is an easy thing to graph, right? If I give it to you in this form, y equals mx plus b, you can tell me the y-intercept is 6, the slope is 4. You could draw that real quick. That would be easier to graph than this one up here, which you wouldn't be able to tell me that as quickly. Understand? So I'm going to test whether or not we did this correctly. And I'm going to try and make you believe it by opening a brand new program, not a brand new program, but a separate program, and I'm going to have it graph x cubed. Oh, no, I'm not, unless I turn this on. X cubed minus 5x, right? There's the graph. And then I'm going to have it graph the line that we just got. What was the line we just got? 4x plus 6. Now, what should I get when I do this? A line that's going to be where? At -1, 2 on the graph right here. This thing should pop in, and it should look like it's tangent to the curve there. Whoa. What was the original function? Oh, I forgot the 3. What was the original function? No. No. This is it. 3x cubed minus 5x. What did I forget? Oh, jeez. I was about to get a huge vote of no confidence right there. There we go. You can still do it. I mean, you can still do a vote of no confidence. What's that? I'll get a raise. Please do it. Okay. So there we go. I'm zooming in on it so you can see it. All right? So I'm feeling pretty good about that. This program actually has, this is free, it's called WinPlot. I don't know if it runs on a Mac, but it has some pretty cool stuff in here. You can actually do a tangent line where you can slide this thing around. Let me make this, -1 is where I wanted to start. And then what it does is, it does a secant line. Whoa. No, it doesn't. I need to mark that point. 1, tangent base point. There we go. Then secant. There we go. But this base got moved. Why does it keep doing that? Yeah. Keeps changing my base point. Well, I'm not going to sit here and do it. But see, this is a secant line right now. The red cursor is one point. The blue one is my base point. And I'm moving it around. And so what you can do is you can tell, okay, give me the tangent there. And it'll actually show you the tangent there. So if I get this to work, I can show you that the computer would verify my blue line. But don't worry about it. Okay, the algebra on that problem was a little bit more complicated than what I normally do for a first example. Having to use a rational zero test and synthetic division is going to come up less frequently than just factoring something would. So that's good news, right? All right, but at least you've seen like what sort of thing you could face. Now let me do another example. Grab my book. We will figure out later on like what this means geometrically, like what the tangent line is going to turn into when we talk about like like an object moving through, position versus time and like what that slope means. But let's just get the mechanics of this down first. All right. How about this one? Find equation of tangent line to the curve y equals square root of x plus 3 at 1, 2. I think you'll like this one a little more than the previous one. All right, so what am I going to bring in here? What do I start with? Define the slope. Define the slope. So the slope of the tangent line will be equal to the limit as x approaches a of f of x minus f of a divided by x minus a. Do you know what a is here? A is 1. So how about x approaches 1, f of x minus f of 1 over x minus 1. Let's now replace f of x with what it is. What is f of x? Square root of x plus 3. What is f of 1? 2, so minus 2 over x minus 1. And you can now let me know whether or not we're good with all that set up there. All right. Who has a question? Anyone have a question? What is the form of this limit? 0 over 0. Check it real quick. 1 plus 3 is 4. Root 4 is 2. 2 minus 2 is 0. 1 minus 1, 0. So we have a form of 0 over 0. I'll just put it on the side here. The form here, we get 0 over 0, right? Algebra or trick? Yeah, so you're thinking conjugate? That's the right thing to think. The conjugate is usually saved us whenever we saw square roots. So I'm going to take this limit, I'm going to multiply the top and bottom by the conjugate, which is root x plus 3 plus 2 over root x plus 3 plus 2 again. Which is the limit as x approaches 1 of x plus 3's first and then minus 4. Right? X plus 3 is what you get when you go here to here, and then the middle ones are gone. The last two multiply to be what? Negative 4. All over all that. But I'm not going to multiply the x minus 1 through to this root stuff. I'm going to leave it alone. Why? That's what I want to cancel, right? I want that to go away. And what do you know? The top is x minus 1, isn't it? This up here is x minus 1. And the x minus 1 over x minus 1 will cancel. So you're left with the limit. X approaches 1. I saw this happen on the test a couple of times, so when I was grading them. When you cancel that factor on top, what's still there? 1, okay? Don't just all of a sudden not write a fraction anymore. And then on the bottom, what's there? Square root of x plus 3 plus 2. So go ahead and take your limit now. you get 1/4. Because this becomes 1, that's now 4. Root 4 is 2. 2 plus 2 is 4. 1/4. So 1/4. Now, let me ask you a question that might be a little bit more profound, a little more deep, all right? Unless there's a question. Does anyone have anything question-wise on this? We're not done, right? Yes? Right here? Just 3 minus 4? Yep. I didn't do anything crazy. Yeah. You're wanting it to be harder than that, right? All right, so let me ask this question. It's a little more profound. If you were walking along this function right now, okay, imagine you got this curve, right? This function, what was it? Square root of x plus 3. You're walking along, and you're standing at the point 1, 2. And let's just say we're reading the function like from left to right, the way that we would read a book in the United States, right? Then if I'm standing there and I'm facing this way, and I go to take another step, I'm just going to start to walk in that direction. Am I going to go up or down? What? Why? Why? Because it's a square root function? Because the derivative, because the slope of the tangent line is positive. Now remember, that tangent line is touching the graph at that point, isn't it? And the answer is positive 1/4, which means the slope of that tangent line is angled up a little bit, which means that if I go in that direction, the rate of change in that direction is positive, right? Now, you could have said that because it's a square root function and maybe you know what that looks like, but imagine we can do this for any function though, right? Without even knowing what it looks like, we can go to a single point and we can say, at that point, what's that slope? So you can try and figure out where things are going up or where they're going down, right? Does that make sense? All right. That's the slope. We need the equation. So here comes the equation. The equation comes from y minus y1 equals m times x minus x1. Here, y1 was what? 2. M was 1/4. X1 was 1. So there's your equation of your tangent line. I should have put there tangent line. The equation of the tangent line is this. I'm going to go ahead and solve for y. I have to add 2 to both sides. So 3/4 plus 2, 7/4. Don't put a decimal there, okay? We're in calculus now. We should be able to add fractions. So adding 2 to both sides. Any questions? Yes? No? Sure? Okay. Well, let me pose something to you here. Where's the problem I just had? Where is it? Did I go too far? Okay, let me give this back to you. I'm going to ask you this question again. But let me scratch this end part out here, okay? So find the equation of the tangent line to this curve at part A. 1, 2. Part B. Let me see here. 6, 3. Part C, what's my next perfect square here? 16, I'm trying to make these nice. 16, so 13, 4D, 22, 5, E, 33, 6. That should be good. So tell me what would suck about this. How much paper it's going to take, right? Because you got to set up for each one of these, you have to set up the limit to get your slope, right? So you got to go find out the limit of this, which we just did this problem, didn't we? Then we go and we figure that out, figure out the tangent line, we're done. Now we start the problem over, and we have a new limit, yes? We set it up, our A is different now. A is what? 6 instead. And set it all up and do our thing. And then the next one we set it up again. A is 13. Do it all the work, right? Next one. Right, and this would take a lot of time. There has to be a more efficient way to do it then. The problem with doing it this way is every single time I go to the next problem, A to B to C to D to E, I keep changing what in the problem every time I do that? I keep changing the A, right? So why don't we do something clever? Why don't we try and figure out what the slope of the tangent line is for an arbitrary value? In other words, don't let A be 2 or 1 or 6 or 13 or 20. Let's just let A be A. And see if we can come up with a slope of a tangent line that makes any sense. So follow me, see if you can see what I'm kind of getting at. So I'm just going to put a note here, this sucks. So how about we do it at this point? Instead of giving you a point, how about A, f of A? So I'm not actually going to tell you what the A is. So what would the slope of the tangent line be there? Limit, right? X approaches what? A of f of x minus f of A, because I'm not telling you what A is, all over x minus A. Yes? That's the definition of the slope of tangent line. The only thing that you know in this problem, though, is what f is, right? And like you know what this function is. By the way, the y is replaced with f of x, right? That's okay? All right. So I can actually tell you what f of x is, and I can actually tell you what f of A is. Let's write them down. This is the limit. X approaches A. X approaches A of f of x. What is f of x? Square root of x plus 3? Yes. Minus what is f of A? Square root of close A plus 3. Right? That's what f of A is. Since I don't know what A is, I plug A into the function, square root of A plus 3. All over x minus A. Let's see. Go ahead and let me know here how you're doing with that. Whoa. Ask me a question if you're not following something there. This right here? Okay, so let's forget the calculus for a second. Here's a function, okay? If I say plug in 2, you plug in 2 right here, right? Say plug in 10, you plug in 10. I'm saying plug in A. So you plug A in right here, you get square root of A plus 3. What was happening before is that this was actually, when you plugged in a number, you were getting a number out, right? In the previous one, we plugged in, what, right here, f of 1. We plugged in 1, we got 2. This time, I'm not letting you lock down a value on 1. I'm not telling you what it is. Or we're acting like we don't know what it is. That kind of makes sense? Okay. What's the form of this limit? 0 over 0. Now, why is it 0 over 0? Let x turn into a right now. Right? Just replace your x's with a's. You would get a plus 3 underneath the root minus the same exact thing. That's 0 over a minus a. That's 0. So you have 0 over 0, which means you need to do some algebra. And you like this algebra. Apparently on the test you liked this problem. You did well on this problem, right? You enjoy the conjugate. You enjoy it. Yes, so let's conjugate this thing. Top and bottom. What is the conjugate that we're going to come in with? Square root of x plus 3 plus square root of a plus 3. Square root of x plus 3 plus square root of a plus 3. Limit a goes to, x goes to a, sorry. What do we have on top there? So we do this times this first, right? X plus 3. Be so very careful here. The middle terms are gone, right? We already know that about the conjugate. The last two that multiply, you just get the a plus 3, but what was sitting in front of that a plus 3? A minus. And so I better put that a plus 3 in parentheses. If I don't do that, I may get into some trouble with that, right? All of this over x minus a, and I'll put it in parentheses, times all that junk down there, which I'm not going to multiply through, because I'm really hoping that that x minus a is going to cancel. Is that x minus a going to cancel? Yes, because when I do clean this up right here, this becomes x plus 3 minus a minus 3, just distributing the negative through the parentheses. The 3's cancel each other out, and so you're just left with x minus a on top. X minus a divided by x minus a, reduce that down to a 1. So I'm ready for my next line, but I'm out of paper. Well, you know what I mean. So I'm going to go to the next page. Limit. X approaches a. What's on top? 1 over square root of x plus 3 plus square root of a plus 3. And now let's let x become a. Let x approach a now. What do you get? 1 over? Yes, I'm going to write it this way first, though. So that's just letting the x become an a. And now you have a root plus the same root. That's 2 of those roots. This was a little bit more complicated as far as the algebra was concerned. Would you agree it was a little worse than the conjugate we did earlier? A little bit? Lot bit? Same? Good. If it's the same. But what is so great about this is that this is the slope of our tangent line, right? Where? At A. So now you want me to actually come back and do this? Sure. The slope of the tangent line here, if A, this x-coordinate is our A, all I have to do is go back here and replace this with 1. What's 1 plus 3? 4, square root of 4. 2 times 2, 4, that's 1/4. That's what we got earlier, isn't it? But now I just go back, and you want me to do this one now? Sure. I'll just plug 6 into this. So just come back here. 6 plus 3, 9, square root of 9. 3 times 2, 6, 1/6. You want me to do the next one? 13? Sure. Go over here. 13 plus 3, 16, square root of 16, 4, 2 times 4, 8, 1/8. Now I could knock it. You give me 1,000 of them, and I can knock them out. well, by the end of the weekend. But you see how much more efficient that is than having to do each of these one at a time? But the sacrifice that we have to make is that the actual limit can be a little bit uglier because this f of a is not a number. It's actually going to turn out to be an expression involving a and whatever the function's doing. But it's more useful if we can do it that way. I hope that that made sense. I'm not going to finish this problem out because I don't want to now go and, each one of these, this is y1, y2. You go in, do your slope formula, you find the equation of each one. But I think I made the point. Let's see if I've made the point. Have I made the point of the value of what I just did? All right. How much time do we have? We have lots of time. What are we supposed to cover today? I don't want to get too far behind. Thinking about what we can do right now. I don't know if I want to move on or not. The only reason I wouldn't want to move on is because it could confuse you, but I think that this would be a great chance for us to do an in-class group assignment. I think this would be a good opportunity for that. Okay? So I'll turn the lights on. I'm going to put 2 problems up on the board. I want you to work in groups. I'm going to take it as a quiz grade. All right? Thank you. Okay, problem number 1. No, everyone turns in their own. All right? Find slope of tangent. It's time till the end of class. Yeah. Tangent line of f of x equals 1 over x plus 1 squared at x equals a. All right, that should probably take you the rest of the class. So let me just be clear on what's being asked here. I give you a function. I don't want the equation of the tangent line, okay? That's using this thing. All I want is the m. And the reason I'm only asking for the m is because I don't want it at a specific point. I wanted it in general. So this is like the last example I just did. You're not going to replace a with a number. A is going to be a. And you've got to set up that limit formula for these 2 functions in the algebra, and that is going to be exciting. This one is the one that everyone had problems with on the test. One of the ones everyone had problems with on the test. Something similar to this. Okay, enjoy. I'll come around and answer questions after you struggle with it for a little bit.